Good morning, my name is Jenny Sun, and this is Kasia, Oleske, and our senior design was the alignment of gold nanorods in the plane by an electric field device. So here's a little bit of overview of what we're going to talk about today. First, we're going to introduce the project, talk about why we did what we did. We're going to go through a bit of the project itself, talk about our results, talk about some conclusions we can draw from there, and talk about the future work that we can maybe do on this to make our project better. So an introduction of what we did. So first we had to, we used gold nanorods, to which we attached a polymer matrix in order to make them orientable and alignable. And then we had to design an electric field device in order to actually align these nanorods. And we needed to be able to pass our samples underneath this device, underneath an electric field, in order to align them. And so the rest of our project was to actually, after we built our device, run our samples through them and then test to see alignment. And so the way we would test for alignment would be, there's a couple ways. First way is using absorbance. So nanorods absorb, when they're randomly oriented, have two absorbance peaks, which means they absorb two different ways of wavelengths based on their size. And so if we actually manage to align them in the plane, if we polarize incoming light, we should be able to see the disappearance of one or the other of these peaks due to resonance. Another way we could actually see alignment would be to use SEM. By taking images of the nanorods, we could visually inspect them and see how the orientation was. And then finally, we could actually take these images, and there's special software that allows us to find the average angle of all of the nanorods in an image, finds the standard deviation within those angles, and then the larger the standard deviation, the smaller the alignment, and vice versa. So our motivation for doing this project was namely that it had never been done before. Nanorods are easily alignable, especially metal nanorods are easily alignable, but nobody had ever managed to align them in the plane. What people usually do is put a sample between two electrodes of an electric field, and that way they're aligned perpendicular to the plane. But that doesn't allow for all the features that we want, all the functions that we want. So if we were successful in aligning them in the plane, we could create new coatings that would, based on that absorbance of specific peaks of specific wavelengths, we could allow for new and interesting coatings that have applications in optics or in even things like sunglasses or films, coatings for windows, for green applications. And so in order to actually design our electric field device, we first need to model the fringe lines coming out of our electric field. This is because we're actually aligning by the fringe lines of an electric field. We're not putting it through, we were running our samples through the fringe lines. And so in order to actually model that, we had to solve the two-dimensional Laplace equation, which yielded the electric field in the y direction beneath our electric field. And so here's a model of a couple of those fringe lines right here. And so we knew from literature, from people who had done the alignment perpendicularly in the past, that we needed an electric field strength of about 90 to 110 volts per millimeter. And so based on our distance of about 10 microns away from our electrodes, we knew we needed about 350 volts through our electrodes in order to actually achieve that electric field. So here's a schematic of our device that we designed. So here it is enlarged. So we have our two electric contacts to our voltage source. And so our voltage source was, we could go up to 3,000 volts. And so we could actually change with anything we needed in there. The electrodes themselves, and then actually our sample holder on a motorized track, which would allow us to pass it through under this electric field. And we had a space in between to keep the distance constant and known, and that way we could always be sure of what our electric field was. And so now Kasia will talk a bit about our samples and our results.
Thanks, Jenny. So now that we have this electric field device, as you can see our final prototype over here to the left, it's time to start making samples and see, hey, what can this device do? So the system we wanted to test were gold nanorods in a PEG matrix. So the first step was acquiring these gold nanorods. So we got gold nanorods from the Murray group, which is a group in material science and engineering here at Penn. And then we put them into an aqueous solution, which basically means we added water as a solvent. And we added polyethylene oxide in order to lower the surface energy and make sure that the particles didn't conglomerate. Then we were able to attach PEG, which, as Jenny mentioned before, polyethylene glycol in order to make the gold nanorods more alignable and polarizable. So our major study was seeing, hey, what's the electric field have to do with alignment? If we increase electric field, does that increase alignment? So as you can see on the left is a SEM image of the control sample with no electric field applied. And in SEM, it's a top view of the sample, so you're only looking at 50 nanometers deep. But our samples ended up being about 100 to 200 nanometers thick. And you can see in the schematic below the SEM image is a cross-section. And so when no electric field was applied, the gold nanorods were just randomly oriented throughout the thickness, which is why they look a little blurry in the image in the SEM. But when an electric field was applied, the nanorods were brought up to the surface because they're attracted to the electric field. Therefore, in the SEM image, they're much clearer. So now that we see this qualitative difference, let's quantify it. So if you look at the table, you can see a definite increase in alignment with an electric field. But we didn't get total alignment. So now we ask ourselves, can we predict the conditions for 100% alignment? So in order to attempt to do this, we plotted our experimental data, and we found two really important things. One, there appears to be a critical electric field strength in order to get any sort of alignment, which matches up with previous research. We got about 110 volts per millimeter needed in order to get any sort of alignment. Now, we want to project an electric field where we get total alignment. Therefore, we set the standard deviation equal to 0 and find out what electric field is needed. So we got an electric field of about 170 volts per millimeter in order to do so. One of our other studies we did was a concentration study. We wanted to find out, should we have more or less solvent in order to get increased alignment? So the short answer to this question is we want to use the least amount of water or whatever solvent you want to make these samples in order to get the best alignment. This makes sense because in order to get alignment, you're orienting the gold nanorods. And if there's increased solvent, they can just float around and there's more time for evaporation, which is what we relied on in order to lock the gold nanorods into place. You can also see that in the lower concentrations, you see the circular orientation. This is attributed to the polyethylene oxide in the solution because these form circular micelles in 3 dimensions. But when PEO dries, if there's any residue, the gold nanorods will want to orient in circles instead of being aligned in the electric field. So in the future, we'd prefer to use either no solvent or minimal solvent in order to get increased alignment. So, in conclusion, we were the first people ever to be able to orient gold nanorods in the plane. In previous research, people just kind of wrote it off. They said it was experimentally unattainable and just didn't even try. And so it's really exciting because now we have all these interesting optical and polarization, absorption properties that were never before achievable. And we can even confirm this not with just 2D analysis, but with cross-polarizers. So you can see in the image on the left is our oriented film, and it glows under birefringence. And the control sample is on the right with no electric field, and it has minimal to no birefringence, which means we truly did get alignment. And not just, these films are just not the only part that's interesting. Our electric field device, as you can see, is kind of small, but it's totally able to be scaled up for industry. Think about it. You could have big vats of solution, you could pour it into a channel for a sample holder, have a big machine that basically just takes the electrodes and moves it across. So it's something totally feasible for industry. It's not just something we can do in a lab. There's plenty of future work to be done on this project, including studying nanorod linking, increasing the nanorod length to see how that affects alignment, increased UV-vis testing, and trying trying to use different types of channels in order to get better control over the thickness. So thank you very much, and we'd love to answer any questions.
And what are some uses, potential uses for the aligned gold nanorod?
So there's plenty of uses. One of them is optical computing. So these gold nanorods, when oriented in the plane, could be used for chips or electronic devices. They could also be used for sunglasses because of their polarization properties. That's more of a low-tech application.
There are even some green uses. So they're tunable because you can change the size of the nanorod you use, and it'll absorb a different wavelength of light. So if there's, for sunlight, we know we like our buildings with lots of windows, and that's great in the summers, but in the winters, if it gets cold, you can have something that, for heating, to reduce heating costs, you can have it, other way around, I'm sorry. In the summer, to reduce cooling costs, you can have it absorb certain wavelengths of light that sunlight would produce. So that the inside would remain cooler, and your windows just absorb the light and get rid of it entirely.
This changed some other production techniques, like making graphene or other industries besides gold?
Yes, so anything that is able to be polarizable or able to have an induced dipole would be able to use this technique.
Any other questions?